Okay. So, dear participants, I welcome you all again to the last day of this NanoDev 2021 for the first session. This session is on silicon RF technology and it is to be delivered by Dr. Ayan. He is from SCL Mohali. Dr. Ayan received his BTech degree in Electronics and Communication Engineering from Maulana Abul Kalam Azad University of Technology, West Bengal in 2005. Later, he did his master's from NIT Durgapur. He joined ISRO as a scientist and subsequently was posted to SCL Mohali, Chandigarh. His research interests include design and development of various bands, passive microwave integrated circuits and antennas, for example, L band, S band, C band, X band, K band. And particularly for these applications, he used silicon-based MIC and RF MEMS technology. His field of expertise include fabrication of various MEMS-based sensors and evolving their test strategies for different applications. He has engaged himself in high-frequency device modeling and development of passive devices for Terahertz applications using silicon micromachining. He has many publications in reputed journals and conferences. He has authored a book named as Silicon RF Technology, but it is published from Springer. He has received many awards from Department of Space for his involvement and technical contribution in Rajbhasha Hindi. He has shown a keen interest to build a strong communication link between academic institutes and industry. In this context, he has delivered various lectures in the invited talk series of various institutes of national importance. He serves as a reviewer in reputed refereed journals like IEEE Access, Springer Journals, Elsevier Journals. He is a fellow member of IETE and life member of Indian Science Congress Association, IFSC, etc. So with this, now I request Dr. Ayan to share his talk with all of us, and let me thank Dr. Ayan to accept our request to be the part of this NanoDev. Thank you very much, sir. Over to you.
Thank you, sir, for this nice introduction. I'm really grateful to you and the whole organizing committee, as well as I'm really grateful to the director SCL for giving me the permission to share my hands-on experience. So today we will talk about the silicon RF technology and its relevance to the modern era communication. So we start our presentation with a very popular quote from Swami Vivekananda ji. So that is, every new concept has to pass through three stages: ridicule, opposition, and finally the acceptance. It is true for the technical field as well as for the non-technical field. If some technology has its own potential or has a merit, then obviously people has to accept it, whether it is a MEMS, NEMS, or silicon RF technology like that. So people will initially object, people will have lots of questions upon you, but finally if it has a salient features of advantages, then it can prove its own potentiality. So same is true for this SIRF technology also. So we will go to the whole presentation with these outlines. We will come up upon the very brief upon what are we doing here, and then what is the insight of this technology, silicon RF technology. Then we will go to the what is micromachining things. I think lots of speakers from the SCL has already briefed upon the what is MEMS and what is that things, and now I will mainly focus upon the what is the RF flavor of that thing with the silicon substrate. So as we know, this SCL Chandigarh, it is the only center of the ISRO in the northern part. So taking that facility of this SCL, so it has parallelly two fabs are running here. One is 6-inch, another is 8-inch. inch, we can have a flavor of A to Z facility here. You under a single umbrella, you can get CMOS, then MEMS, optical things, everything, and you can start from the very basic things. That means I just want to say start from your design, then you can fabricate those things, and finally you can have your systems after the testing, characterization, then packaging and all these things. So you can have a flavor of a whole system out of this semiconductor laboratory. So that is the beauty of this center. So if you come to the RF technology and with the silicon, normally people will object initially because there was no proven things with this silicon. Or normally for the microwave or the RF people, gallium arsenide, FR4, RT duroid, alumina, these all are the popular substrate. Usually these have been used extensively from the long time, but now the time is going to be changed. Now the silicon has the also potentiality to prove its potentiality for this RF or microwave uses. So there is one proverb that is known as the yesterday's chip is now today's functional block. So that's why people used to say like that. Now people used to think like from system on board to the system on chip. This paradigm shift is going to be happen. Whatever the device we are using in nowadays normal life, so out of the devices, whatever the communication devices are there, most of the devices are going to be fabricated upon this silicon. Now, this silicon has its own potentiality to change its resistivity, and not only that, after changing the resistivity, the whole physics, whole device physics is to got changed. Now you can use the whole that silicon substrate for the RF or microwave uses also. So in the subsequent slides, we will see how this can happen. And so the concept of the system on board now converging to the system on chip, SOP to the SOC. So how miniaturization is going to happen. So that's why people used to call the yesterday's functional block is now today's chip. So that's why earlier we used to think about the microprocessor, 8085 microprocessor and all that things. Now people used to talk about the microcontroller. So now how the device is going to be converged, how the whole system miniaturization going to be converged. And that's why not only for the airborne system but also for the ground-based systems also lots of progress has been happened. And now people are thinking about why not to take this silicon for this integration purpose, monolithic integration for passive circuit also as well as the active circuit, and why not marriage between this active and passive circuit under a single platform. So that's why the beauty of this silicon is there. But if you want to use this silicon for the RF or microwave uses, then you have to think about how I can model that particular substrate. So this comes from the very basic things of the transmission line theory. If you know the very basic of the transmission line, you can model that particular substrate for the RF or the microwave uses also. We know that there are basically three kinds of losses are there whenever we talk about RF or microwave. One is conductor loss, another is substrate or dielectric loss, and finally we talked about the radiation loss. Now, if we are not talking about any antenna kind of circuitry, then this radiation loss you have to tackle by somewhere else. Now, conductor loss, it is obvious for the low frequency as well as the high frequency also, high square R loss. Now, coming to this substrate or the dielectric loss, this is the things which your substrate or which your dielectric material will be the culprit for that. So that key element of what is the main causes of this dielectric loss, that has to be find out. So for that, if you characterize that things, you will find the substrate loss is nothing but a function of the frequency as well as the resistivity of the material, because people have find out that there are basically two kinds of modes propagates through the silicon substrates. If we take the resistivity of the silicon greater than equal to 4 kilo ohm centimeter, then it is known as the high resistive substrate. And if you go to this high resistive or the HRS kind of substrates, we will come to know that it has three basic properties. One is uniform resistivity throughout the thickness of the wafer, then acceptable radial and axial resistivity gradients, and finally the stable resistivity throughout the device processing. That means throughout the various kinds of temperature, pressure, this kind of processing. So coming to these basic modes of propagation, basically two kinds of modes propagates through the silicon. One is known as the slow wave mode, another is known as the quasi-TEM modes. And if you come to characterize this particular silicon for this RF uses, then we will come to know one important parameter called as a dielectric relaxation frequency. The concept of dielectric relaxation frequency comes from the very basic concept of if you take the dielectric and if you apply some alternating field, then you will come to know this particular dielectric will get charged, as well as whenever you remove this alternating field, then ultimately this charge should be ideally removed instantly, but it doesn't happen practically. Or rather, it happens like that. Some charges are trapped. It will take some time, and this much of time is known as the dielectric relaxation time, and from that you can find out the period of that relaxation also. So mathematically it is expressed with the help of this formula Fc equal to 2 pi 1 by 2 pi r into c, where this r and c are coming from the very basic equivalent circuit, or in other words it is equivalent to the resistivity of the silicon as well as the permittivity of the silicon. If you look at this particular basic equivalent circuit of this transmission line, you will find this G and C basically dictates nothing but a leaky capacitor. That means it is indicating how much dielectric loss is incurring into the substrate. So that is the main cause of this dielectric loss. So if by some means we are able to remove this kind of substrate loss, we will achieve higher bandwidth, we will achieve higher efficiency in case of your circuitry, and this R is nothing but the cause of this ohmic loss or the I square R loss, and the change in the current, change in the flux is denoted by this L. Now, what are the different fabrication topologies around the globe is going on if you are readily want to use the CMOS grade silicons? So people used to offer generally. Yes, sir.
Can you switch off the fan?
Okay, okay. Sorry.
Because this air is disturbing, sir. Thank you. Thank you. Also, may I request to switch on your camera, sir?
Okay, sir. 1 minute.
Answer, camera from your. Otherwise, please continue. No issue. Otherwise, please continue.
Okay.
Okay, sir. Now it is okay. Sound is okay.
Now it's okay?
Yes, sir. Excellent.
1 minute, sir.
Ayan sir. Hello. Ayan sir.
Hello, sir. Can you hear me?
Ayan sir.
अच्छा अयान जी क्या गड़बड़ होगी मैं
पता
कॉल
नहीं
कर
सर,
रहा हूँ अयान जी को
मैं भी कर रहा हूँ सर,
ओके
वो बिजी है।
मेरी कॉल जा रही है सर
अच्छा ओके सर, ओके।
फोन उठाया नहीं उन्होंने या तो
दिनों के लिए केवल बहुत जरूरी होने पर ही घर से बाहर जाएं और भीड़ भाड़ से बचें।
हाँ जी सर
Ayan sir.
सर ही इज डूइंग अगेन
Okay sir, okay, okay.
नमस्कार।
जैन सर कैसे हो? आए हो सर? ठीक है सेहत?
Hello.
कहता हूँ
Sorry, sir.
अच्छा अच्छा,
Hello.
ओके सर।
Sir, you are able to
आ
listen
जाना
now?
सर, आ जाना, इधर आ जाना सर,
Hello.
चाय पी लीजिए।
এ মা আজকে আমার কি হচ্ছে গো? Hello.
हेलो
Hello.
हाँ आयान जी we can hear you you can
Okay,
share your
okay.
PPT now
I think there was some network issue.
okay no issues
Okay, okay, sir. Now
please share it again
you are able to hear now.
Yeah,
yes
we are
yes
able to
yes
hear, but we
Sorry
cannot
for
see your
the
screen, sir.
interruption. So these are the potential applications of the silicon RF technology where
so you need to share your PPT
okay. Now, sir, is it visible?
Yes, sir.
Ha. Okay.
Sir, we were at previous slide.
Where we can able to see what are the different potential applications of the silicon RF technology. Basically, there are two topologies around the globe are there. One is known as the top to bottom approach, another is known as the bottom to top approach. So usually this bottom to top approach is very popular, because whenever you are talking about any device like small devices like switches, inductor and varactors, and if you have the potentiality to cope up the final stabilization of that device, then you will come to the next level, that is the circuit level. As for example, suppose if you are through with the switches and all these things, then you can go to the phase array and phase shifter, all these things, and finally you can integrate that phase shifter with the antenna, and you can able to get the phase array antenna, and that's all. So another important new gateway of this silicon thing is the terahertz things. So that is possible because this silicon has the potentiality to use up to the terahertz level also. That means if you go beyond 100 gigahertz, you will come to know that there are several factors will come into for the communication purpose. One is that is the maximum power handling capability. Another important thing, it will come just like a absorption or the attenuation factors. So normally people used to avoid this kind of communication earlier, though lots of research have been going on into these particular things, but lack of solid state devices, just like from 100 gigahertz to this 1000 gigahertz, because whenever you are trying to develop some system, you have to come up with the whole solution with this system. That means you have to be in your hand with the active devices, passive devices, your antenna, that things, and the whole transmission chains, whole communication link has to be established. So now that is possible with this silicon micromachining things. You can get an idea of these things if you are
Answer, we lost your voice, sir. Answer.
I think he is having some network issue. Is he presenting from SCL, sir?
No, sir, he's presenting from home, I think.
Okay.
SCL I can take care, but at home.
Yeah.
hello.
Yeah, answer, please.
I think there is some network issue. That's why even that slide is.
But we can see your slide, sir. This loosely defined 1 mm lambda greater than.
Hello, Manish sir.
Yes, sir. Yes, sir.
You just take care. I am coming back.
Okay, sir. Okay, sir. Okay, I will take care, sir. Thank you. Participant, please wait. There is some network issue with the presenter. So we are waiting for that. Answer. Answer. Yeah. Our speaker is trying to join again, sir. Please wait. Sorry for the interview. Ayan, sir. Ayan, sir.
कर रहे हैं सर, लॉगिन कर रहे हैं वो, पे हूं मैं।
Broadband coming. Now you are able to see me also.
Now you did, yes, we can see.
Yes. Now you can say this particular micro electromechanical system, it's a acronym for MEMS is the acronym for Micro Electromechanical System. In the 1980s, this acronym first coined, and in different countries, it's named like different things. I think my earlier speaker, Dr. Jasprit, has already explained all these things beautifully yesterday's session. And you can say this is nothing but three aims for miniaturization, multiplicity, and finally the microelectronics. And if you ask somebody what is the device dimension you can achieve with this particular thing, you can think about it's nothing but a size of your RBC or WBC, red blood corpuscle, or just like a human hair. So there is one slide intentionally I have put just to make a comparison between these things, how this miniaturization can happen with this silicon technology and micromachining technology, and how we can achieve the different sizes or scale and dimension we can apart. So this figure basically shows how these MEMS or micro electromechanical systems can give a flavor of this miniaturization. And we know the different components of this MEMS is nothing but there are basically four basic block diagrams are there. One is micro sensors, another is microelectronics, finally the micro actuators and the microstructures. There is a interlink or communication between all these things, and we need obviously some power supply for this all these systems. And If somebody asks where MEMS can take its footstep, the answer is the every corner of the human life, starting from the biological things, even at the optical domain, communication, everywhere. It can and spread its wings everywhere. So that's why, according to the uses, the classification has been made. If it is used for the RF or the microwave communication, it is known as the RF MEMS or the microwave MEMS. If it is used only for the physical sensing all these things, then it is a physical MEMS or only sensor these things like that, navigation things and all these things. So you can and get an idea how different. Here I have put only few glimpse of circuitry for micro motors, micro robots and all these things. Similarly for the optical MEMS also. So there are huge amount of application area. There is a very wide application area with the help of this silicon technology. Even if you enter into this RF, you will come to know that what are the different applications of this silicon RF technology or silicon on MEMS technology, where you can use your mind or you can use your thinking to build a whole system. Basically, there are four basic fabrication technologies are there. One is bulk micromachining, another is surface, and finally the electroplating and the wafer bonding. From the bulk micromachining, from the name itself, you can get an idea that if the bulk of the material, bulk of the silicon is removed from the actual substrate, then you can get this kind of bulk micromachine feature. Just like, as you know, the potassium hydroxide or TMH, these kind of solutions are used extensively in the semiconductor fab to get an etched pattern of silicon. And finally, we will see how this kind of patterns are used for this antenna and all these high frequency applications. So you can get this kind of patterns with the help of this MEMS technology, and finally can be removed extensively with a significant amount. Now coming to this surface micromachining, this is the one additive process, you can say. So this particular additive process will offer you to get hanging structures which is not present in the normal microfabrication or CMOS technique. So that is the beauty of this surface micromachining. Yesterday lectures you have seen that there are lots of cantilever applications were showing. So that kind of applications, that kind of structures can be built up very easily with the help of this surface micromachining. Though you know that lots of challenges are there, whether from the design point of view, rather than from the fabrication point of view also, and finally the system realization is really difficult for all those things. But apart from these bottlenecks, you can get an idea of these hanging structures out of this surface micromachining process. And if you want to have some thicker substrate, if you want to make some filter kind of things and high Q filter, then you have to think about how can I maximize my Q, how can I maximize my Q factor, because you know from the very basic theory of this Q factor, if we can maximize the volume of the whole resonator, then there is some option that we can maximize the Q factor also. So that is the way, by means of that, wafer bonding has come into the picture, and by this wafer bonding techniques we can stack multiple silicon wafers together and different pattern silicon wafers also with the help of anodic bonding or with the help of eutectic bonding. Though this particular classification have own merits and demerits obviously are there. And finally, if you want to have a thicker metallization, you have to go for the electroplating. Because you know, in the standard microfabrication technology, normally people will offer you up to 1 micron, 2 micron, but in MEMS or in silicon RF technology, sometimes you need thicker metal like 20 micron, 30 micron, 50 micron. So that is the problem which can be solved with the help of this electroplating technology. So with all these things, we can get the micro machined feature, which are very much useful for this RF or the microwave application. And now if you come to this micro machining things, you will come to know this whatever losses we have already discussed about. So out of that, the main important thing which we can reduce significantly, so that is the dielectric or the substrate loss. So that dielectric or the substrate loss can be minimized significantly with the help of this micro machining technology. And for that, you can get lots of advantages like less losses, surface wave can be minimized, leaky wave can be minimized, and finally you can get a higher efficient and circuit and higher bandwidth circuitry out of that. So what are the bottlenecks of the RF design? As you know, for the low frequency, what are the challenges are there? In the high frequency, that are common, but in addition to that, you have a noise portion, you have a frequency gain bandwidth product. This has to be optimized. Then apart from that, you know how the losses, radiation losses has to be tackled. That also has to be seen. So there is a trade-off between multiple parameters, and for that you have to use your mind, not only for the simulations and the design always cannot happen. And you know, as a blessings of this silicon RF technology, nowadays you know lots of planar transmission line and lots of planar antennas are going to be used knowingly or unknowingly in our daily life, just like in our smartphone, in our Bluetooth devices, and all the handheld or wireless devices. Even in the future, IoT system also, it will be used extensively because of its several merits like lightweight, low profile, it's miniaturized device, and it's very much suitable for the airborne system also. Even it can be used for the space, satellite, or even the mobile communication. But it has also some issues, like it is offering a very low gain, and its directivity is also low, as well as its radiation efficiency is also not up to the mark. So that's why people are coming with this silicon RF technology or this silicon micromachining technology to get rid of all these issues with the help of this silicon micromachining technology. We know from the very basic theory of this transmission line, the basic equation lies here. This Z is nothing but a root over R plus j omega L divided by G plus j omega C. Now, for a lossless transmission line, this R and G will become very nearer to 0. So finally, this Z naught will be the square root of L by C. So that is the goal of any RF or microwave engineer. How can you reduce this dielectric loss with the help of this silicon micromachining? How you can and get rid of this bulky silicon beneath your antenna, so that effectively your antenna will see a permittivity of around air, because it is seeing nothing but a thick column of air and a very thin layer of silicon. So obviously the effective permittivity will get reduced, and it will be very nearer to the epsilon R. So finally you can suggest that my circuitry will have a better radiation efficiency, better bandwidth, and finally I can give you some very low profile antenna with all of these promises. Not only for that, if you are thinking about 3D stacking or multi-layer stacking kind of things, so that 3D or vertical integration is possible with the help of the silicon RF technology, because here with the help of this micromachining technology as well as with the help of this wafer bonding, you can have a stack of multiple wafers, where with the different wafers containing the different building blocks of your whole system. So that's why people have reported up to 94 gigahertz this millimeter wave and sub-millimeter wave. Lots of research is going on into this particular area. So different silicon wafer they have processed differently, and finally this stack can be bonded with the help of this wafer bonding technique, and finally you can get a very low footprint but a highly efficient circuitry with the help of this 3D vertical integration circuitry. And you know, whenever you are talking about any antenna, microstrip antenna or planar antenna, you know, different feeding techniques have been discussed, and we know out of those different feeding techniques, one of the important technique we used to call as a aperture coupling. Though this particular technique is a very promising technology, but its realization is really very difficult with the help of the PCB technology. So that's why people used to come to the silicon technology or micromachining technology for that. Because if you look at this particular 3D profile, you come to know there is some slit is there is some feed line is there, and finally some cavity has been etched and your antenna is there. So stacking of all these things is possible, and there, if there is some misalignment is there will be some cross polarization will be there will be some spillage of the electric field will be there. Finally it will get to the losses and your antenna will be radiation and wise less efficient. So that's why this is the only solution for this aperture coupling techniques, and people have reported up to 94 and 100 gigahertz. If you look at the Professor GM Ravi's work, you will come to know that how much work he has done in his lab. And coming to these antenna array problems, you know, the single antenna cannot serve your purpose always. If you want a much more gain, much more directivity, you have to go to the obviously to the antenna array. But the problem of this array is the one is feeding, second one is the mutual coupling. This mutual coupling can sometimes be a cross coupling, it may be a negative coupling. So from one antenna to another antenna, it may hamper in just like a negative interference, so that your whole radiation pattern, your whole gain will be diminished instead of increasing. So that kind of spurious coupling or unwanted mutual coupling can be removed with the help of the different channel opening or air pocket opening with the help of this micromachining technology. And simulation study as well as the practical realization has shown even up to 110 gigahertz this technology can be utilized extensively to reduce the parasitic couplings between the different antenna elements. And I will say this will be very much useful for the massive MIMO or the MIMO, multi-input multi-output, this antenna technology also, which is going to be used extensively for this IoT application. One of the important component of any microwave or RF system is the filter. As I have already discussed, the filters figure of merit relies upon its quality factor. So if you want to enhance the height of the filter, you have to go for a thicker wafer or thicker cavity or deeper cavity, you can say. So that is possible with the help of this silicon micromachining, or specifically I should say with the help of this bulk micromachining, as well as with the help of this wafer bonding technology. Because these are the things which ultimately used for to replace the different communication elements already in the building blocks, as already we have seen in the functional chains of the communication chain of the normal super heterodyne receiver. So there you can replace these microwave filters with the conventional filters with the promising Q factors. And coming to this phased array or the smart antenna technology, if you entered into the smart antenna field, the antenna going to called or named as a smart whenever it can change its frequency, it can change its polarization, when it can alter its polarization quality, or it can change its radiation pattern. So antenna called as a smart in different sense or in different reconfigurability. according to the situation, if it can behave just like an intelligent and human being, then we used to call it as a smart antenna. So phased array antenna, sometimes it is the backbone of that smart antenna. So before going to the smart antenna technique, we should know about this phased array antenna. And this phased array antenna, this comes from our daily life, common life problem. Suppose if I am giving this lecture to audience of say 50 people, and if somebody doesn't like to hear, though he is listening to the lecture in his laptop, but actually he is not getting anything. But if somebody wants to really learn something, wants to interact with some technology, want to gain or cognizance out of that technology, then he will get. So smart antenna is just like that. If I want to communicate with you, I will put my radiation pattern, I will put my antenna oriented towards you only, not towards X, Y, or Z. So that is the beauty of these things. And now this scanning lies there only. Earlier, it used to happen with the help of this mechanical scanning array. Now, with the help of this electronically scanning array, lots of advantages are there. Now you know there is no wear and tear problem. It's lightweight. That's why it's getting all the advantages. And as I have already told how the smart antenna behaves, so that's why the backbone of the smart antenna is nothing but a phased array antenna. With the help of these input phase shifters, you can get this smart antenna out of the system, and this phase shifter can be built up with the help of several switches as well as the transmission line, which can be realized with the help of this silicon RF technology. Now people have reported all this silicon RF technology and how it is efficient. You can get a comparison chart out of that. Here you can see how this loss factor is very low for this MEMS circuitry or silicon RF technology, and the isolation it's really very high, and power consumption is very low also. And power handling, though this is the only bottleneck of this technology, the power handling is very low. So this can be mitigated with other techniques. So lots of research is going on for mitigating this technique. This is the only bottleneck of this MEMS technology. It cannot handle much more higher power, just like your watt, kilowatt, that kind of things. But if you characterize your circuitry for several higher frequency also, you will come to know the how much low loss you can get. Even for a single bit of the phase shifter, you can get only around 3 dB insertion, whereas for a gallium arsenide you can get around 9 to 10 dB applications. Now, with the help of the technology available at our SCL, just like silicon as well as the upcoming this gallium arsenide technology, we can get a flavor of the whole silicon RF technology or the monolithic integration in future. Just like you can get a flavor of this CMOS, ASIC, all these things, and in rest of the circuit that you can get your antenna and all these things. So there is a good combination, there is a good bonding has to be happen between all this circuitry, and finally you can get a very miniaturized, smart, tiny device out of that things. And these are the practical applications of the phased array antenna in space. I think we have heard about the messenger. It was a mission from 2011 to 15 where various radiating elements like around 26 elements in the X band it was used. So this is the practical applications of the phased array antenna in the space also. And coming to this silicon RF technology, whenever you start your journey, you have to come across the characterization, modeling, and then finally you have to understand whether your particular substrate can be for different multi-band operation or for not. And so for that only, from the very scratch, we started with this very basic block diagrams of the communication application, just like balloon, power divider, all these things. Even we characterize multi-band circuitry like 1.575 and 2.680. This single power divider can be operated. Then we come across a few systems like that. This is known as the receiver direction of arrival systems. So DOA, these systems consist of you can see this is the power divider sections and this is the branch line coupler. So a marriage between these, all these things has happened with the help of this silicon RF technology. And finally, if you give this antenna input here, you can get the whole system out of these things also. Whether this particular silicon technology has the potential to realize the antenna or not, or whether it can have a potential to sustain the ultra wideband feature or not. So that's why we have characterized for 3.1 to 10.6 gigahertz this whole wideband feature for that also. And now coming to this technology, whenever you are demonstrating any technology or you are going to model this technology, you have to think about some packaging techniques and inter between this shorting this thing also you have to think about this thing. So that is known as the TSV, through silicon via. This is just a similar like a PTH, plated through hole, just in it is used extensively in the PCB technology. So that TSV technology also we have designed, we have modeled it also and fabricated it also. So thanks to our whole fabrication team for this also, because it was really very much challenging. And not only for that, whenever you are plating this particular TSV, so there is a very high chance for the void formation. So this particular TSV things, it's a very important thing for the packaging technology. And not only for that, you know that this through silicon via, it just not like a short circuit. It's not shorting your top layer to the bottom layer. Rather, in the high frequency, it will offer some inductance, it will offer some capacitance and resistance also. So that's why whenever you are using this TSV, you have to get ready upon with the model things also. Now, this silicon RF technology is best for the implementation of the LNA and different components also. So for that, you know, the one of the very basic component is the inductor. Now, this inductor is really very essential for any RF engineer, which is not available normally with the CMOS circuitry, because in the CMOS you can make the inductor now, but you cannot make a high Q inductor. What is possible with the help of this silicon RF technology and with the help of this MEMS, you can make this kind of hanging structure, and this hanging structure will get reduce your substrate loss ultimately. So that's why you can get the high Q inductor out of these things. And people have demonstrated inductor like that also, where you can understand how high Q can be achieved for the inductors also. And coming to the very primitive component of this silicon RF technology is nothing but a MEMS switch, and this MEMS switch can be of different types. Here in our SCL, we started our journey with the capacity shunt type MEMS switch, and after a lots of struggles, we have seen how this particular switch is going to be realized and how it is characterized. And finally, you can use this particular switch for the phase shifter, for the phase shifter antenna, phased array antenna, or for any reconfigurable kind of things. Now coming to this reconfigurable, what I was talking about, this reconfigurability can be out of this frequency, can be for the radiation pattern, it can be for the polarization, and it can be hybrid of anything. So reconfigurability, earlier it was with the solid state technology, earlier with the use of this PIN diode, varactor diode. Now MEMS comes as a promising element for removing all those counterparts, and it is replacing all those things with the help of this RF MEMS technology. Now, this particular silicon RF technology can be used for the biomedical applications also. several antenna on chip or on chip antenna can be fabricated for SoC implementation. And recently NIT Durgapur and CSIU Chandigarh has come up with their design, and we have fabricated all these things, and they are happy for their performance also. These are used extensively for their on-chip applications, and they can. There was characterization with the human phantom mimicking solutions also we have made, and then we have tested in our BDD division in SCL itself, and finally with the help of some flexible substrate like liquid crystal polymer LCP substrate, we have made this kind of things also out of these things. And at the end of the day, it can be said this RF MEMS or this silicon RF technology, it is obvious for the future wireless application. If you go to the any literature, you will find that this normally CMOS varactors is a very popular things. Now people are coming with this MEMS varactor because it has a Q factor of around 200 to 300, and it doesn't have a significant leakage also. Not only with that, it has a tuning ranges typically spanning from the 5 to 50. So with all of these promises, you can say if you want to see the future of the wireless communication, if you want to be with this 4G, LTE and then 5G, ultimately you will come to know that this silicon technology for this RF application, whether it is IoT or 5G or higher frequency, just like terahertz frequency, this is obvious ultimately. And finally, we should go to this technology, though some bottlenecks are there, though some hurdles are there. So with these hurdles only, we have to move upon, and finally we can get out of these things. And with all these things, I just want to conclude my presentation with these references. Thank you very much for your patience. Lots of disturbances were there initially. I'm sorry for that.
Okay.
Thank you, Anshul.
Thank you, sir. So, a question answer.
So participants are requested to write their question in Q&A section. Can you see it, sir? Ayan.
Hello, sir.
You can see questions in Q&A section. Did you find it?
Yes, I am clicking, but no question was. How many questions are there, sir? Here it is not showing.
Yeah, I am also not able to see, sir.
Because
What was the size of that capsule type antenna?
Capsule type antenna, the capsule was 26 millimeter long, and this width was 10 mm.
10 mm, okay.
10 mm.
Or 26 centimeter long.
Actually, there was two variants, sir. Excuse me, sir. There was two variants. One was with the 7 cross 7 mm, and another was on the LCP antenna. It was for the 26 cross 10 mm.
Okay. Okay.
Because at that particular application, we don't need any positive gain. Or you will get only negative gain only, because here for that application you have to use the receiver belt tied up with the patient's abdomen. So it's a very near field communication kind of things.
Okay. Participants, if you are having any question, please type in Q&A section. If no question, then we shall close this session. Did you receive any questions, sir?
Answer?
No, yes.
Okay, so let's close this session, Hodaji.
Yes, sir, sure.
Okay, so thank you, Ayan, for accepting our request to share your expertise with all of us. So thank you very much for joining us for this NanoDev 2021. So now I request participants